Hello everybody. Today we will be going over linear transformations. This is part of week 4 of Carnegie Mellon University's 21-41. You can find their schedule online, so let's dive right into it. So, linear transformations. Let's first look at this by considering the matrix 1, 2, 3, 0, -1, 4, as well as the vector 1 and -1. So we will be trying to apply a linear transformation on it by doing matrix multiplication, AV. So we write A out and then V, and we multiply it. So the dimensions of A is 3 by 2, and the dimensions of V is 2 by 1. So we're expecting a product of the dimensions 3 by 1, as you can see here. You can work it out by yourself, but it's basically just row times column, row times column, row times column. So let's try to describe this transformation more generally using x and y. So we take the same matrix A and we write xy, and we can view the transformation on xy. So it would be this x, 2x minus y, 3x plus 4y, as you see here. So the way we denote this is the transformation A, TA on xy gives us the 3 by 1 matrix x, 2x minus y, and 3x plus 4y, where A is the matrix we have above, 1, 2, 3, and 0, 1, -4. So let's view an example. So an example problem. So given the transformation xt, xy equals to x, 2x minus y, and 3x plus 4y, and y equals to x1, y1, v equals to x2, y2. Let's find transformation of u plus v. Well, we know that linear transformations addition is you basically just add the two together. So x1 plus x2, 2 times x1 plus x2 minus x1 plus y1 plus y2, and so on and so forth. So this seems simple enough. So let's get into the bread and butter of today's lecture. So we'll be talking about linear transformations, and that every matrix transformation is a linear transformation. So we will be dealing with matrices this lecture. So consider if A is a n by n matrix. Consider transformation from vector space Rn to vector space Rn. Then the transformation of x with A will still be in Rn, as exemplified by the notation of the transformation. So let's look at an example. This will be example 6.5 in the textbook. So we define a transformation that goes from mnn to mnn by transpose A. So we want to show that T is a linear transformation. So how would you do it? Well, basically, we just need to prove the two properties of a linear transformation, that you can add them together, and you can apply scalar multiplication. So TA plus B equals to TA plus TB. Similarly, TCA will equal to CTA. Yeah. So keep in mind that you will, if asked to prove that something is a linear transformation later in the homework, you will need to use this kind of proof. So, and later in this section, we will also see that a differential operator and the integral are also linear transformations, but I do not feel like writing the proof down here, so that's something you just need to know. You can try to prove it by yourself. I'll leave it here as an exercise for you, and it's very similar to the proofs of that we've shown before. You basically just use addition and scalar multiplication. So now we want to look at the properties of linear transformation. And we are given a theorem, Theorem 6.14 in the textbook. So let T go from the set V to the set W. We have 1, that T to the 0th vector is still the 0th vector. B, T to the negative V gives us negative T to the V, where we can see that the scalar C is basically negative 1. And that C, Tu minus V will equal to Tu minus TV, because we can just apply B on the addition. So property A will be very, very useful in proving that transformations are not linear. You will see this on the homework for week 4, so keep in mind that this is quite useful. So now we would like to look at an example. This is example 6.55 in the textbook. So we consider the transformation from 0 space 2 to P2 such that T to the 1, 1 equals to 2 minus 3x plus x squared, and 2 in transformation of the column vector 2, 3 will give you 1 minus x squared. So we will want to find T to the negative 1, 2, and T AB. So this is actually very easy. You might want to pause the video and try to do it. All right, so now I'll do it to you. So basically what we want to do is, well, since we're doing linear transformations, we want to achieve a linear transformation from 1, 1, 2, 3, and we want to get it to negative 1 and 2 by using scalar properties of the linear combination. So we'll find that C1 gives us negative 7 and C2 gives us 3. And basically we just plug this back into the equation where T of 1, 1 gives us 2 minus 3x plus x squared, and T to the 2, 3 gives us 1 minus x squared. So we just multiply it by the factors and we simplify it, and we'll get negative 10x squared plus 21x minus 11. So now TAB is quite similar. We take a similar approach where we similarly construct a linear combination that gives AB equals to C1, 1, 1 plus C2, and 2, 3. So what we want to do here is we use A and B as constants. As you can see, C1 will become 3A minus 2B, and C2 will give us B minus A. And then we plug it back in similarly, but I'm kind of lazy. So now we want to look at Theorem 6.15, where let's consider the linear transformation T from V to W, and the set B from V1 to Vn be a spanning set of V, which is the domain of the transformation. Then the transformation of B will give us the transformation from V1 to transformation of Vn, and it spans the range of T, which is basically V. So please, I would like the viewers to prove this. You can pause this video for a second, and afterwards I'll show you the proof. So basically we just have to fix a vector V in the set V, and we know that the vector V must be in the form of C1 V1 plus blah 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 blah, so on and so forth. And by the properties of linear transformation, we can see that we can apply a transformation to all of them, and it would be just a scalar. So hence, V is in the span of B, and therefore transformation of V is also in the span of transformation of TB. Yeah. So now let's move on into a newer topic, the composition of linear transformation. So I would like us to recall the composition of matrix transformation in the previous section. So we know that if TA equals that, then A must be the matrix of this. So let's start with the definition. If T and S, where T ranges from U to V, and S goes from V to W, and they are linear transformations, then the composition of S with T is S of T U equals to S of TU. So we're assuming here that U is in U and that the range of T is contained by the domain of S. If you don't understand this, please pause the video and think about it, and hopefully you understand. So let's look at an example here. Example 6156 in the textbook. So we let T that ranges from R2 to P1 and S that goes from P1 to P2 both be linear transformations defined by TAB equals to A plus BX and S of P of X equals to X of P of X. So what we want to do here is find S of T of 3 over negative 2. So this is actually very easy. I would like you to pause the video and do it. But basically what we do, we just plug A and B into T of A and B, which will give us AX plus A plus B x squared, which will give us 3x plus x squared. I'm sorry. Yeah. It will give us 3x plus x squared. So let's consider the theorem 6.16, where we have two linear transformations as in the previous example. And we know that if these two are linear transformations, then the composition S of T is also a linear transformation. So let's try to prove this. So we let U and V be in the set U, and that C is a scalar. So using addition, we know that S of T of U plus V equals to S of TU plus S of TV. And it would be the same for scalar multiplication. As I said previously, this is a very common proof for this kind of application. And so basically the final remarks of this video is that linear transformations are also associative. Linear combinations are also, linear compositions are also associative, provided that the compositions make sense. Basically, if the domains fit the spans. So thank you all for watching this video. I hope this video helped clarify some questions on linear transformation. If you have any questions, please post in the comments and I will respond to you. Happy studying.